Hey everyone, this is Connor Mead with the Calculation Center with our first video in our calculus series. In this video we'll be going over the basics of differentiation, by which I mean we'll go over the rough idea of what the derivative does, what it is, and some important examples that we'll need to know going forward. So what I've done here is kind of sketched out the fundamental image of single variable calculus. The idea here is, given a blue curve here, we want to know what differentiation does to it. Now, the derivative, denoted by this d dx, is applied to this function f, and it turns this blue curve into this red curve. The important thing to know here is that this red curve basically gives us the rate of change of the blue curve. By that I mean, if we look at some point here, say x0 that I've chosen out to the right here, we can construct the tangent line at x0 f of x0. That is, we can construct the tangent line that just glances off our graph above x0. Now this line will have a certain slope m. In this case, m is clearly positive because it's going up. Remember that a slope is positive if it's going in this direction, negative if it's going like this, and 0 if it's going flat across. But this x0 has some slope m, and then the derivative at the same point will therefore have height m, and that's how we generate the derivative. It's just basically we look at every single possible point, compute what the slope would have to be at that point, and plot it as a graph. Okay, so important notes is that these kind of peaks and valleys, where the kind of tangent line would just glance off, like this and this. Notice that these both have slope 0, so the correspondence here is between these peaks and valleys and the zeros of the derivative. So 0 of the derivative will be a peak or valley in our original curve. So that's the basic idea, is that this curve, this differentiation operator takes functions to other functions via this rule of their slopes. Now, some important derivatives that you're going to need to know. We'll just briefly go over these. You'll often be told these for exams, or maybe you'll be expected to know them, but these are just basically the fundamental building blocks for our derivatives, because these are, generally speaking, the functions we care about. So if your function is a monomial, that means it looks like x to the a for some constant a, then its derivative is going to be equal to a times x to the a minus 1. Okay? So let's just look at some important specific examples here. For example, here, we're looking at x, which is, of course, also equal to x to the 1. So in this case, a is equal to 1. So we bring the 1 down in front. So this is actually 1 times x to the 0. But of course, x to the 0 is equal to 1, no matter what x is. So overall, this thing is indeed just 1. So the derivative of f of x is equal to x is 1. Similarly, the derivative of the constant function f of x is equal to 1. This is equal to x to the 0. So again, when we were to apply this formula up here to it, a is equal to 0, so it's equal to 0 times x to the minus 1. But of course, 0 times anything is equal to 0, so this thing is just 0. Now here are just some more typical examples to show that the formula works whenever we want to use it. X to the 20 will of course just be a standard application of this formula. A is equal to 20, so we bring in the 20 down in front and decrease its power by 1. That's basically what the formula says. So it's 20 times x to the 19, because 19 is 20 minus 1. And this example here, x to the pi, so pi is about 3.1415. It's a very irrational number. We can't write it down precisely. X to the pi, however, still functions like any other number. You just bring the pi down, so it's pi times x, pi to the minus 1. Okay, so that would be about 2.1415. But this rule still works even when you're dealing with weird numbers like pi. And the last thing to be careful of is if the a is negative, like x to the minus 5, a is equal to minus 5, we do the exact same thing, we bring the minus 5 down, but the important thing to remember is when you reduce a negative number, it becomes a bigger number in some sense, right? So it's x to the minus 5 becomes minus 5x to the minus 6. Just to remember that subtracting off, it doesn't become x to the minus 4, for example. It becomes x to the minus 6, okay? And these are the rules for monomials. We'll deal with in the next video how we can, the rules of differentiation that allow us to combine all these results and how we can basically differentiate any function. In this one, we're dealing with, you can kind of think of this as monomials. This will be exponentials, by which I mean these have to do with exponential functions and the inverse of exponential functions. So if we have a function f of x, which looks like b to the x, so maybe like we could have like 2 to the x here or something, then this would imply f prime of x is equal to b to the x times the constant number, the natural log of b. And remember, the natural log of x is the inverse function to e to the x. So in this case, if f of x was equal to 2 to the x, this would become natural log of 2 times 2 to the x. Okay? And a very important example, more important than this b to the x example, is actually you need to know this f of x is equal to e to the x. Now, e is, of course, equal to 2.718 something something something. But the important thing is that the natural log of e is equal to 1. So therefore, when you apply this formula, this natural log of e will disappear, and you'll just get e to the x again. This is almost the defining property of the exponential function. It's a function which is equal to its own derivative, and it's the only function satisfying that condition. Except for maybe like, sorry, there's a larger family that actually I should say, but this is the fundamental example. Okay? And the last example in this exponential section is f of x is equal to natural log of x. In this case, f prime of x is equal to 1 over x. This one is, of course, a little surprising, but it is nonetheless an important example to know, and if you don't know it, you probably won't be able to figure it out easily. Okay? And the last family of derivatives that you should know are trigonometric, which have to do with trigonometric functions like cosine, sine, and tan. Trigonometric. Okay. Now there's so these can be sometimes a little tricky to remember, but I'll just go over them briefly. F of x is equal to sine of x, then f prime of x will be cosine of x. If f of x is cosine of x, then f prime of x is equal to minus sine of x. If you're having some trouble remembering where the minus sign goes in these examples, just do a quick sketch of cosine of x, and do a quick sketch of sine of x. The important thing to remember is they both look like squiggles, except sine of x starts at 0, and cosine of x starts at 1. And notice that cosine of x is actually like, it's flat here, but it starts going down pretty immediately, so the derivative should be negative. And in contrast, the sine of x is positive at the start, and is positive for a while. Therefore, when we're differentiating cosine, we need to pick up a negative sign. When we're differentiating sine of x, we don't pick up any negative. Okay? And now these last ones you're kind of just going to have to be familiar with. I don't think there's any easy way to remember them. You can, of course, derive them if you know the proofs, but if you don't, you're going to have to just know these ones, or perhaps you'll be given reference to these in your exam. But f of x is equal to tan of x, then f prime of x will be 1 over the cosine of x squared. And remember, this is the numerical square, not repeated application of the cosine function. F of x is equal to the inverse sine of x. Then f prime of x will be 1 over the square root of 1 minus x squared. Similarly, the cos inverse of x, its derivative is minus that. It's minus 1 over the square root of 1 minus x squared. And the inverse tan of x is equal to 1 over the square root of 1 plus x squared. Okay? So I would say these are the most important examples to know off the top of your head. I don't think there's anything else you really have to know for an exam that you wouldn't be told. But we'll go on to how to combine these results and how kind of we can use this information to basically differentiate anything in the next video.